Welcome to this lecture series in group theory. Last time we looked at Wilson's theorem, which says that if P is a prime, then this congruence holds. So basically the remainder of this guy when we divide it by P is P minus 1. Okay, today we'll be looking at another very beautiful result regarding primes, but first these are the problems. And this is a problem which I'll sort of use in this lecture. So that's why this is marked with a star, not because this is hard, but because I'll use it, sort of use it. Anyway, so here is a very simple lemma that is basically at the heart of the proof that we are going to give for the Fermat's little theorem. Before we state Fermat's little theorem, let's just get this out of the way. So P be a prime and choose A, an integer, with these constraints. So it is in this set basically. Then we define a map which we denote by F sub A. A is coming from here. So this map consumes some element of this set and produces this product. And there's already a problem with this map because AX may not even lie in this set. For instance, if A were equal to 2, then 2 times x can easily fly off away from this. For instance, 2 times p minus 1 is not here. It's greater than p minus 1. So what I really want to say is, whatever this number is, this is a truly true integer. So what you do is you take its remainder modulo p. So that I will write with a slight abuse of notation as that. So this is supposed to mean the remainder when ax is divided by p, where by remainder I mean something that lies in this range. Now this cannot be 0. Since x and a are both in this region, the product of a and x cannot be divisible by p, because neither a nor x is divisible by p. So the remainder is indeed in this range. So this makes sense. The map now makes sense. Okay. So the claim is, then, let me bring a grid because otherwise, yeah, so then FA is a bijection. So since these are finite sets of the same size, it's as good as saying that FA is surjective, or as good as saying that FA is injective. Any injective function on a finite set to another finite set of the same size has to be surjective and hence bijective. So we'll just show that FA is injective. So proof. So to show injectivity, let's say FA of x equals FA of y, which means the remainder that ax leaves modulo p is same as the remainder that ay leaves modulo p, which is same as saying this. And this is the thing that one has to realize. Although I could just skip that step and directly write that p divides ax minus ay. Since ax and ay leave the same remainder when you divide them by p, of course p divides ax minus ay, which implies p divides a times x minus y. But since a is relatively prime with p, we get p divides x minus y. Why is a relatively prime with p? Because a is in this range. So any number in this range is relatively prime with p. Okay, so this means that x equals y. Why is that? Because x and y are in this range. If you take a difference of two things here and let's say you take the absolute value, you can assume that x is greater than y, doesn't make a difference. So that number will again lie in this region unless the two numbers are equal, in which case the difference will be 0 and this will indeed hold. So the only way this can hold is that x equals y. So if a takes two different points, or rather 2 points to the same image, then those 2 points are equal, and that is precisely what injectivity means. So this implication implies that f is injective and therefore f is bijective. So we are done. Oops. So this proof is complete. And now let's go to Fermat's little theorem. So it's a very simple statement. It says that if p is a prime, then for any integer a, we have this congruence holds. Okay, so let's prove it. So if p divides a, then it's clear because both sides are leaving remainder 0, and hence this basically reads 0 congruent to 0 mod p, which is of course true. So may assume that, sorry, my writing is not aligned. For some reason I can't see the grid very well. Give me a second. Yeah, so if p divides a, then we are done. So assume p does not divide a, that is a is relatively prime with p. Okay. So we may assume, it hardly matters though. Here in this lemma, we really didn't need the fact that a is between this range. We just needed that a is relatively prime with p. That's all that we needed, but okay, since I have written it that way, I'll just use it that way. So in fact, we may assume, we may further assume that a is in this range. Why? Because any integer after, any integer is modulo p in this range. So you can just replace a by its, replaced by an integer in this range, which is congruent to a, and the statement really doesn't change. So I hope you see that. So it's something that we don't really need to assume, but because I wrote this statement in this particular fashion, I'm sticking to it. Okay, so now as we proved in the previous proposition that fa1, this set, is nothing but this set. So maybe I should have written a few more entries, but okay, I hope you understand what I mean. So this is all integers from 1 up to p minus 1, and this is the image of 1 up to p minus 1 under this map. And since this map was a bijection, this set is same as that set. So which implies the product. Okay, let me not use this notation. Let me just write it in a more direct way. So this product is equal to that product. This is true as integers. All right. But now, since this is true as integers, we can just write this also modulo p. Okay. So what is fa1? fa1 is the remainder that you get when you divide a by p, but since we are going modulo p, fa1 is as good as a fa2. So there is an fa2 here, which is kind of hidden in the way I've written fa2 and then fa3 and so on. fa2 is nothing but 2a modulo p. So this is 2a and then a 3a and p minus 1a congruent to 1, 2, 3. Let me just write p minus 1 factorial. We could use Wilson's theorem, but there is no need. So this is nothing but p minus 1 factorial times a to the p congruent to p minus 1 factorial mod p. And now you could either use Wilson's theorem, or you could just say that, well, this guy is relatively prime with p. Each factor of this guy is relatively prime with p, and therefore this is also relatively prime with p. So you can just kind of cancel this off. Relatively prime things can be cancelled off. We mentioned that before. So this gives us a to the p is congruent to, what have I done? Sorry, this is a to the p minus 1. This is a to the p minus 1. Right, there are only p minus 1 terms here. this is a to the p minus 1, and after cancelling this off, we get that. And we could just stop there, but multiplying by a on both sides, we get that. Right, so very nice proof. It's not an obvious idea. But there are much more obvious proofs of Fermat's little theorem. And we'll see another proof using group theory. Anyway, so I hope this was clear. And a very simple corollary, in fact, what we have already proved in the course of this argument is the following, that if p is a prime and a is an integer not divisible by p, then this congruence holds. This is what we ended up showing here. So I just wanted to, take note of that. Okay. And Fermat's little theorem can be used to make computations easier and faster in these kinds of problems that I'm going to discuss now. So this huge number, we want to divide by 59 and find out the remainder. And we can do it without using Fermat's little theorem, but let's see an illustration as to how one can go about such things. So we know by Fermat's little theorem that 5 to the power 59 minus 1, 59 is a prime. This is congruent to 1 modulo 59. Which implies 5 to the power 58 is congruent to 1 modulo 59. And since this is a 1, it's so comfortable, we can just square both sides and we get, what is this? What is 58 into 2? We just squared both sides, so we still get that. And it is 5 to the power 16, I think 116, yes. This is congruent to 1 modulo 59. And now we are really interested in 5 to the power 119, so we multiply both sides by 5 to the power 3. So we get 5 to the power 119 is congruent to 125 modulo 59. And this remainder we can calculate by hand. So whatever is the remainder of this guy, the remainder of this guy is, I think, 7 modulo 59. So this is the remainder when you divide this huge number by 59. Alright, so I guess this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.